A velociraptor and a protoceratops lie tangled together in sandstone, frozen in the middle of a fight. Nearby rocks preserve dinosaur nests, delicate embryos, small mammals, lizards, and skeletons that still hold their bones in place. These fossils come from Mongolia's Gobi Desert, one of the driest regions on Earth. So, how did such a harsh landscape preserve an entire Cretaceous ecosystem? The first answer is surprising. The Gobi was not always as dry as it is today, but the full answer is more interesting than simply replacing desert with jungle. When Velociraptor lived here, parts of the region really did contain enormous dunes. They also contained seasonal ponds, temporary streams, patches of vegetation, and sudden floods capable of turning loose sand into a deadly trap. The ancient Gobi was not one habitat. It was a changing mosaic, and the rocks preserve every part of that contradiction. Start at the Flaming Cliffs, also called Bainzak, in southern Mongolia. The red rocks exposed here belong to the Djadochta Formation, one of the most famous dinosaur-bearing rock units in the world. Much of it formed during the Late Cretaceous, roughly 75 to 71 million years ago, although correlating every exposure precisely remains difficult. This is the world of Velociraptor mongoliensis and Protoceratops andrewsi. It was not the humid tropical forest often imagined as a standard dinosaur habitat. Geologists have found clear evidence that wind pushed sand across broad dune fields. The strongest clue is crossbedding. Instead of forming flat layers, grains inside the sandstone lie in sloping sheets. Each sheet records sand sliding down the sheltered side of a dune. As the dune moved, one layer buried another. Stack thousands of these surfaces together, turn the sand into rock, and an ancient landscape of migrating dunes appears. At Ukha Tolgod, another extraordinary Djadochta fossil site, geologists have identified both organized dune layers and more chaotic masses of sandstone. Those structureless deposits are interpreted as sandslides. Parts of steep dune faces suddenly collapsed and rushed downhill. That sounds extremely dry, and it was. The Djadochta environment was probably semi-arid, with evaporation often winning the struggle against rainfall. Yet buried between the dune deposits are layers of mudstone and siltstone. Fine mud does not settle out on a racing dune. It collects in quiet water or on wet ground. These layers point to shallow interdune ponds and lakes that appeared when water gathered in low areas. Some may have lasted only briefly. A heavy storm could fill a depression, feed a temporary stream, and trigger a burst of plant growth. Then the water would shrink or vanish, leaving cracked mud and exposed sediment behind. The desert returned, but not before recording the wet episode in the rocks. Calcrete supplies another clue. This is a hard, calcium-rich material that develops within soils, often where rainfall is limited and evaporation draws dissolved minerals upward. Its presence supports a dry climate, but it also proves that surfaces sometimes remain stable long enough for soil to form. This was not an endless ocean of constantly moving sand. Picture the landscape as a dry basin with dune ridges on the horizon. Tough vegetation grows where roots can reach moisture. Low areas hold water after rain. Protoceratops moves between feeding grounds on its powerful hind limbs and shorter forelimbs, using its deep beak to crop plants. Velociraptor, far smaller than its movie version, crosses the same ground as a lightly built predator around 2 meters long. Exactly what plants covered the Djadochta landscape is difficult to reconstruct because plant fossils are not abundant there. A lush forest would contradict the sedimentary evidence. A completely lifeless sand sea would contradict the animal community. The safest reconstruction lies between those extremes. It was a stressed but productive dryland ecosystem, with life concentrated around scattered resources and seasonal moisture. This mixture of dry dunes and sudden water also helps explain the exceptional fossils. A dead animal on an open desert surface does not automatically become a fossil. Scavengers can tear it apart. Sun and wind can break down the remains. Sand may cover the bones slowly, then uncover them again. The spectacular Gobi skeletons required something faster. At Uka Tolgod, many animals appear to have been overwhelmed by sudden masses of sand. A dry dune can collapse under its own weight, but water may make failure even more violent. Intense rain can soak part of a slope, add weight, and loosen the grains. A wall of wet sand can then surge downward, burying a small animal before the skeleton is scattered. Some fossils are preserved in postures that suggest they were alive when the sand reached them. That does not tell us the exact weather on a particular day, but it supports rapid burial rather than slow accumulation. The most famous example is the Fighting Dinosaurs specimen, discovered in 1971 at Tugrican Shire. It preserves Velociraptor mongoliensis, locked against Protoceratops andrewsi. The Protoceratops has caught one of the predator's arms in its beak. Velociraptor's enlarged foot claw lies near the herbivore's neck. The pose is direct evidence that these two animals physically struggled. Their exact cause of death is less certain. Scientists have proposed several scenarios, including burial by a collapsing dune or another sudden sand-moving event. Whatever the final sequence, both animals had to be covered quickly enough for their intertwined bodies to remain together. The fossil is often presented as a snapshot from a sandstorm, but an ordinary storm depositing grains little by little may not have buried two large, struggling animals fast enough. A sudden slope collapse, perhaps associated with rainfall or unstable wet sand, offers a more forceful explanation. It remains a reconstruction, not a witnessed event. The Gobis' nests tell a similar story of evidence being reinterpreted. In 1923, an expedition at the Flaming Cliffs uncovered dinosaur eggs and a strange, toothless theropod lying above one clutch. Protoceratops fossils were common nearby, so researchers initially thought the eggs belonged to Protoceratops and that the theropod had died while raiding the nest. It was named Oviraptor, meaning egg thief. Decades later, an embryo was discovered inside the same general type of egg. It was an oviraptorid embryo. Other adults were found positioned over similar clutches, with their bodies and forelimbs arranged like brooding birds. The supposed thief had probably been attending its own nest. Those fossils changed our understanding of dinosaur reproduction, but they also reveal something about the environment. Nests require surfaces that remain exposed and stable for at least part of a breeding season. Their preservation then requires burial before erosion, scavenging, or weather destroys them. The Djadochta landscape could provide both. Long dry intervals created nesting ground. Sudden sediment movement sealed some nests into the fossil record. Still, the Djadochta Formation is only one chapter in the Gobis' history. Other Cretaceous rocks in Mongolia record environments with stronger river influence. The Nemegt Formation, famous for animals such as Tarbosaurus, Gallimimus, Saurolophus, and Dinochirus, contains sandstone and mudstone deposited in river channels, floodplains, and other wet settings. Its channel fills, ripples, eroded banks, and layers that become finer upward were made by flowing water, not migrating desert dunes. The exact age relationships between every Gobi formation are complicated, and some environments may have existed in different basins at overlapping times. That makes the central lesson even clearer. We should not imagine the whole region flipping from one uniform habitat to another. Rivers, dry plains, dune fields, ponds, and floodplains could shift across the landscape as rainfall, drainage, sediment supply, and basin geography changed. Even the name Gobi can mislead us. Today, it describes a geographic region with a cold, highly continental desert climate. It does not mean that every rock exposed there formed under modern desert conditions. The modern desert is simply the landscape that erosion has cut into much older environments. The world around Mongolia also changed dramatically after the Cretaceous. Mountain building across Asia altered atmospheric circulation and blocked or redirected sources of moisture. The retreat of ancient seas, global cooling, increasing continentality, and the rise of major plateaus and mountain systems all contributed to the long-term drying of Central Asia. The modern Gobi developed much later than Velociraptor, so when we uncover a dinosaur in the Gobi Desert, we are not necessarily uncovering an animal that lived in the Gobi Desert as we know it. We may be looking at a resident of a dune field broken by temporary ponds, or an animal from a broad river floodplain that now receives almost no comparable flow. The red sandstone around Velociraptor does confirm an ancient desert, but the mud between those dunes records standing water. The Calcrete records soil and seasons. The nests record stable ground. The complete skeletons record sudden burial. Farther west, river deposits reveal an entirely different Gobi, filled with channels and floodplains. The desert did more than preserve these worlds. It disguised them. Beneath today's dry surface lies evidence that the Gobi has been many landscapes, and some of its clearest memories of water are the dinosaurs that the sand refused to let go.